Welcome to session number 4 in the series Digital Circuit Design using VHDL. Now in this previous session number 3, we had discussed some of the details of VHDL language, and what we want to do is look at the entire flow of synthesizing, right? So I'll introduce some more concepts, but we will do this live, right? So now what you have over here is is uh, is a PDF which is for this particular board, right? This is now called Nexus 7 or Nexus A7, right? So this is the Nexus A7 board, is the same as the board which I have earlier shown you, right? So let's see. Okay, so this is the board which we are talking, right? And this board is same as this Nexus A7, it's just renamed. So we are going to use this I'm sorry, this data sheet, right? So let's go and see what we're going to do with this. So the whole goal of this is to design some circuits using VHDL, so whatever information we have. So I will call this as digital circuits. So we are going to do digital circuits using VHDL, right? So this is what we want to do. Okay, so now I'm going to make a half header. So first thing I'm going to do is I'm going to make a half header, and using this two half headers, I'm going to make a full header, and then I'm going to make an n bit header. Now I want to keep n bit as generic, right? So I can scale the width of the word at any point of time, right? So I will make an n bit header. Okay, so let's get started with this. So you have to first launch Vivado and then create a project. So it's kind of slow, I think. Yeah, here it comes. Okay, so this is a wizard which will guide you through. We have seen this earlier also, and we will call this as sample circuits, right? And it's going to be stored here. I'm going to say next, and it is going to be a RTL project, right? Next, let's say I'm going right. So next, I can leave this sources off for now. All I have to make sure is that the target language is VHDL and the simulator is mixed. Remember, the test benches are going to be in Verilog while the circuits are going to be in VHDL. That's why it is called mixed here. Next, constraints we will add later. Next, okay, we have to pick up a device. We know our device is a general purpose FPGA of RTX family 7, and then it has got 324 pins, right? And it's a speed grade of -1. So this leaves me with these. So these are called filters, right? So I've set the filters and I'm going to use this one. Next, okay, so my project is created here. So this is going to be slightly slow. Okay, now what do I get from this data sheet? Okay, so let the project get created. Okay, so it is a complete description of various various implementations you can do with the board, right? So I'm going to look for a diagram where I see the pinouts of the FPGA, for example this one, right? So let's zoom in. Okay, so remember I told you that, let me just go and make sure you are seeing what I'm seeing. Okay, so remember I told you that there are over here, okay, over here there are these switches which are 16. So I'm going to make a 8-bit adder. So I have 8 here as word A and 8 here as word B, and the output is going to be 8 LEDs here and then one LED, the extreme left, I'm going to use as a carry, right? So this is what I'm going to do for addition right now, a binary addition, right? So these are listed in that same diagram, right? So let's go ahead and see. Okay, so this diagram, this FPGA numbering is done. Now how is this done? I'll tell you. Okay, an FPGA package has got ball grids here, right? It's a ball grid array. Okay, and it goes both ways. There's rows and columns. Okay, so now these pins are labeled this way. You go from, let's say, 1, or rather you can go from, okay, you can go from 1 to 1 2 3 4 and like that. Okay, and then you can go A B C D like this, right? So you go alphabet this way and this way. So a particular pin is going to be a particular number, a letter, for example C2. So C2 would be this one, right? Or if I say B3, so B3 would be this one. Okay, now these pins are over here, right? So for example, if I look at switches, so if I look at switch number 0, it is J15, L16. So you know where it is going to be. You have to refer to that L, row L, and then 16 column, so that will give you a L16. So these are connected to these switches here, right, on the board, and there are 16 of these switches here going from J15 to V10. Similarly, LEDs which are on top of that, they go from H17 to V11, right? So these are these LEDs. Okay, so I'm going to use this as input. So I'm going to use this 8 up to T8. I'm going to use, so up to R13. So J15 to R13 is 8, and then T8 to V10 is another 8. So I'm going to use word A and B, and then the sum is going to be from H17 to, let's say, 4 up to LD7 or U16. So H17 to U16 would be my output word. Okay, and I'm going to start with half adder, and then I'm going to build a hierarchical design, which is going to be a structural design, a structural style of architecture, and I'm going to build a n-bit adder. So I'm going to keep a 4-bit adder, but this n would be programmable, right? Or you can do 8-bit adder and then programmable. So let's do that. So this is open here. Okay, and I'm going to add a design source. Okay, so add a source here, and I'm going to create a design source, and I'm going to create a file, and I'm going to call this file as half adder, same as the name of the entity. Okay, so this is half adder, and the location is the local location, so I don't have to do anything. Say okay. Only thing is I'm going to change this library to my CKTS. So this is my circuits, right? And then say finish. Now once I finish that, I have got the entity name as half adder, and the architecture name I'm going to use is HA, and here I'm going to add the pins. Okay, so let me make sure that you are getting the same screen as I am. Okay, so we are on the right path. Okay, so in half adder we have got 2 inputs, A and B, and then you have got 2 outputs, which is basically sum and carry, right? Sorry, didn't type it. Sum comma carry. Okay, and this sum comma carry is out. So I have 2 inputs, 2 outputs, and I'm going to say okay. So that would be created here. Okay, and I'm going to double click this one to open it, and what I'm going to do here is I'm just going to add a little bit of comment here, that VHDL code for half adder. Okay, so I'm writing a VHDL code for half adder, right? And this comment, I can just get rid of this comment. Okay, and I have entity already written for me by this Vivado, and I'm going to write just the output. So I'm going to have sum is assigned. Okay, sum is assigned. I can say A XOR B. That's a half adder sum, right? And then carry is assigned A and B, right? So if both are 1, then the output is going to be 1. Otherwise, the output is going to be 0 for carry, right? So A and B. Okay, so spelling mistake, A and B. Okay, so we are done with this. Just want to be sure that if the text is visible clearly. So this is the first run. I might not know this, but let's go to properties or settings and go to the text section. Okay, so go to general. Let's look at text editor. In the text editor, let's look at the fonts. Where is the fonts? Okay, there is a fonts and colors here, and the background, forefront, foreground, this is the color, that's the size. So I'm going to make it 14. How come I don't have this shown up? I want to have a text editor. Just one second. Settings, this is 14. It's changing over here, but how come it is not changing over there? Apply, let's make them bigger. Apply, did it change? Yeah, it did. Okay, so let's make this 16. Apply. Okay, so slightly bigger and you can see it more clearly, right? So this is my code. Okay, so next thing I'm going to do is just check it. So what I'll do is I will just go to simulation and say run simulation. Okay, okay, Vivado is a big software, so you have to get used to this slow, slow speed. Okay, we are all set. First of all, I'm going to remove the previous one, reset it, and I can set this. So I can set this to clock. Okay, so I'm going to set this to clock. Okay, and the leading edge value is, let's say, 1. That's okay. Trailing edge value is 0. And then I'm going to say duty cycle is 50%, and this is going to be 200 nanosecond, right? So this is my clock here. Now here for the second one, I'm again going to force a clock, and leading value is 1 and trailing value is 0, and you will come to know what that is. Okay, duty cycle is 50, and I'm going to use this as a 400 nanosecond. So that's the clock. Okay, and then what I'm going to do is I'm going to set this run for 400 nanosecond. So I get all of them at the same time, and I'm going to say simulate. So if I say view all, I have all the states. Okay, so it is going to be 1 1, sum is 0, carry is 1. 0 1, sum is 1, carry is 0. 1 0, okay, carry is going to be 1, sum is going to be 1, carry is going to be 0, and 0 0, sum is 0, carry is 0. So basically all the 4 states are verified. So I'm done with this, so I'm going to close the simulation window. Close simulation. Do I want to save it? Okay, to close simulation window. Okay, so that is closed. Right, so we have just verified that half adder is working properly. Now if I want to reuse the design, I have to declare this half adder as a component, which I have to do in a library. So we know the library, right? So what I'm going to do is I'm going to generate a package. Okay, so I will go this way. I will say add a source and say next, and here create a file, and I would say this is going to be my circuits is the name of the library. Then I will say here my comp. So my comp is the name of the package. Okay, so I'm going to say okay, and here I'm going to add to the same library, and I'm going to say finish, and constraints I'm going to say cancel. And are you sure you want to cancel? You say yes. Now that would not show up here because I haven't got the IO, so it says non-module files. So what I'm going to do here is going to go here and unreference here. I am going to take it at the top. Okay, now here if I double click this, it will open a blank file. Okay, so now first of all I would say I want to use library, and that library is going to be called IEEE, right? And then I'm going to say use, and I'm going to use a package out of this, which is IEEE dot std underscore logic underscore 1164 dot all, right? Dot all. Okay, so I'm going to press enter. So this is finally done. Then I'm going to say package, 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 and the name of the package. So the name of the package is the same as the name of the file, which I'll call as my comp, right? Is, right? And then I'm going to say end package package, and the name of the package is going to be my comp. Okay, so let me just correct this to be a capital. Sorry, this I want to correct to be a capital M, and the end of the package my comp. Okay, so to me it looks okay because there are no red lines, right? So now what do I do with this package? I have to add a half adder component into this package. So I'm going to copy this as is, Control C, and I'm going to paste it over here and say Control V. Okay, so now entity is not going to be defined over here, so I will call this as component, right? And then is optional, and then say end of component, component. Okay, so here I can add a small text for myself that what is this. Okay, so this is a half adder, right? This is a half adder, right? Just one second, just one second. Okay, sorry for the interruption. Okay, so here we are. Okay, so we have done a half adder here. So let's do a spelling correction. Half adder, not a sadder. Half adder. Okay, so this is my package. This is how I declare a package. Now let's say if I want to create another source here. So I'm going to say here add a source, and I'm going to say next, and I'm going to add a file here which I call as full adder. So this is the same as the name of the entity. Say okay, add to the same library, and say finish. Now in this case I'm going to call the architecture name as FA, and then I'm going to define, okay, then I'm going to define the input pins. Input pins are A, B and C, right? So these are my input pins, and my output pins are sum and carry. Sum comma C out. How's that? Sorry, sum comma C out. Sum comma C out. Okay, so these are my output pins. Okay, so once I'm done with this, okay, I'm going to click OK, and this opens a new design source here, which is called full adder. Now the thing to notice here is this full adder is not the top of the hierarchy. So whenever you see this triangle, that means that this is the top hierarchy. So I have to change that. So I have to go to settings under general, and I will say that for synthesis you are going to use full adder, not the half adder. And then you're going to say for simulation I'm going to do with the full adder, not the half adder. So two changes I have made, right? Under general and simulation, say OK. Okay, so this will shift. It didn't? Yeah, it did. So now full adder is at the top, is the hierarchy. This is the green thing which shows full adder is at the top. Now I'm going to write this full adder. Okay, so I'm going to remind myself that I'm going to write a code for a full adder. So this is a VHDL code for full adder. Okay, the next thing I'm going to do is I need to refer to that library. So my library is called, so what do you call this, your library? My circuits, right? This is the library name. So it is called my circuits. Okay, so I'm going to say my circuits, and then I'm going to use a package out of it, which is use my circuits dot. So this is a dereferencing operator like in C also, and then the name of the package. The name of the package is my comp. Okay, dot all, semicolon. Okay, and enter. So now here I have referenced this. So my component definition for half adder is over here under my comp. So I don't have to do it here in my program. So once this is done, I have to do this. Then I would say that I want to use intermediate signals. Okay, so I have a signal. Okay, and that signal is S0, C0, C1, and then it is of type STD logic, right? So that's my signal definition. Okay, so there are no red lines, means you are doing good. Now let me explain you what would be the structure of a full adder. So the structure for a full adder which I'm going to draw is the following. Okay, I am going to have a full adder defined using two half adders. So this is half adder 1, right? So I'm going to give two inputs to this, A and B, and then it is going to have two outputs, which is sum and carry. Now notice that this sum and carry are the lower pins, right? So when you come to a top level, you can rename this as S0 and C0. Then you are going to give this sum, and then there is going to be C in. So this sum and C in you are going to give as an input to another half adder, HA2, and its output is again going to be sum and carry, right? So this sum you are going to give to the output sum of the top level, and this carry you are going to give to what you call C1. Okay, so now these are the top levels. So these are the signals which I have to use. These are intermediate signals, while the outputs are, this are the inputs and these are outputs, right? So another output is going to be from here. So on the top level I'm going to take this one and this one, and I'm going to do a OR. Okay, so the output of OR is going to be your C out. So the outputs are, so basically the outputs are sum and C out, and the inputs are A, B, C in, and then intermediate signals are going to be S0, C0 and C1, correct? So these S0, C0, C1 are signals, and signals are going to be declared in the declarative section of the architecture. So this is the declarative section of the architecture, which is after is and before begin. So here I have defined three intermediate signals, S0, C0, C1, which basically correspond here to this intermediate signal S0, C0 and C1. Okay, so that's what I have written here. Now I have to just instantiate half headers. Okay, so I can call this one as HA1 is an instance of half header. So I have to write the entity name HALF-ADDER. Okay, and then I have to do a port map. Okay, and in this port map I'm going to map this. Okay, so this can be based on sequence. So if you look at here, if I put this as A, B, sum and carry, so what do I want to give here? A, B, and the sum. So sum will come out on an intermediate signal S0 and carry will come out on intermediate signal C0. Okay, and that's what is over here in our design. So S0 and C0, these are my outputs. So sum is mapped to S0 and carry is mapped to C0. So this is based on sequence, right? So this is based on how you put this. Now if I don't want to follow this sequence, I can do this way also. For example, I can take this thing to the left hand side and I can say carry of the lower one maps to, okay, sorry, there has to be equal to, okay, carry of the lower one, so lower hierarchy, lower in hierarchy is HA, half header. So the carry pin of the half headers, that is called CARRY, carry, right? So it is called CARRY, carry. Okay, so the carry of half header maps to C0. Now the sequence is not important. You can do it this way. So this is perfectly, this should be valid. Positional cannot follow the, okay. So what it wants is the positional would be at the end. Okay, so that's what it means. It means that I have to put them at the end. Okay, so Control X. Okay, then okay, I'll do this way. I will put here Control V, comma. So what it is saying is that first do the referenced ones and then do the so now see the sequence. The first one should be sum, but here I have put carry, and then I can map sum of the lower hierarchy to S0. Okay, so now this is perfectly valid. So what it is saying is first follow all those which are based on sequence, then follow what is non-sequential, like carry has come before sum, while in the definition the sum comes before carry, right? So A, B, sum, carry. Here it is A, B, carry, sum. So this is named referencing, okay, or this is mixed referencing. So a part of it is based on sequence and then a part of it is based on named assignments. So this is a named assignment. So the instantiation, the mapping of the signals can be either based on sequence or it can be mapped by the name. But then if you mix them, then the first you have to do by sequence and then the following one need not follow the sequence, but they are named. So that's also allowed. So the second one is going to be a simpler one, which I will do it just by sequence. I'll say half header, name of this, and then say port map, and here I have A. So A in this case is S0, comma B in this case is C in, comma sum is the same as sum, it's the output pin, and then you have C1. Okay, so you have C1 and then the bracket close and and a semicolon. Okay, If this is red, there has to be, okay, so I have redid the name, so this will be called HA2. You cannot repeat the name. Okay, so now there is no red line. That means that second instantiation is also correct. Now this style of programming is called structural style of programming, and then I can say cout. Okay, this is a behavioral statement, is C0 or with C1, and this. Okay, so this is the entire code for full adder. I have introduced you to how do you do a package, and then how do you declare a component inside a package, and then how do you use that package, the component from that package, and how do you do the port mapping based on sequencing, referencing, name reference, and mixing them together also. And then that's the full adder. Now if I want to test this, so I can just say run simulation. So let me make sure I'm going correct and you are hearing me. So I'm going correct and you are hearing me too. Okay, so I'm going to first delete this, reset it. So I'm going to put in a clock here, force a clock. So in this case I'm going to put a leading value of 0 and the trailing value of 1. So it will start with 0, and then 50% duty cycle and 15 nanoseconds. So that looks fine to me. So that is first clock. Then I'm going to give a second clock. Okay, so in this case I'm going to give a leading value of 0, trailing value of 1, and then I'm going to have a 200 nanosecond. Okay, say okay, and then I'm going to add another clock, force a clock. So leading value is 0, trailing value is 1, and this is going to be 400 nanosecond. Okay, so there are 3 clocks which will generate all the 8 states, and I'm going to simulate for 400, and I hit OK and say view all. So you see for 0 0 0, so I can put a marker over here. Sorry, so this marker over here. So for all zeros output is 1. So I'm not interested in these things, so I can basically press delete for this one. So let's see, and delete for this one, and delete for this one. Okay, so what am I seeing? For all zeros output is 0 and this. Now over here sum is 1, carry is 0. Over here sum is 1, carry is 0. Over here, sorry, over here sum is 0, carry is 1. Over here sum is 1, carry is 0. Okay, hang on, let's check this one. These two are 1. Okay, fine, this is fine. Let's look at this one again, and let's look at this one, and then let's look at this one. So basically I verified that all the states are correct, so full adder is working perfectly fine. So I'm going to cancel this simulation window. Okay, I can discard this. So now I have simulated a full adder. Now I'm going to make a 8-bit adder or a n-bit adder with a default value of n as 8. Okay, so how do I do that? Very quickly, I'm going to create a source. Okay, say next, add create a file, and I'm going to say adder n-bit. Sorry, adder n-bit. So this is going to be adder n-bit, and I'm going to put it in the same library and say finish. Now in this case I'm going to say a and b, a and b. Now here I have already introduced you to a composite word, like composite data types. So let's say I'm going to use 2 words, a comma b. Okay, and these are going to be in, and they are going to be 0. Okay, MSB is 7 down to 0, so I would say 7 down to 0. Okay, now the output is going to be sum. sorry, the output is going to be sum, and this sum is going to be out again 7 down to 0 because I am using 7 bits, right? Or sorry, 8 bits, 7 down to 0. Then I am going to have cin, which is a single bit cin, and then I have a cout, which is again a single bit. Okay, cout, and this one is out. Okay, so I'm all set. So these three signals are the vectors, std underscore logic underscore vector 7 down to 0. Okay, and then these two are going to be just signals, two signals, and say okay. Okay, so now I'm going to declare this as a top level. So go to settings and go to general and set A and B as the top level. And simulation also you set A and B as the top level and say okay. So once you are done with this, this should shift. Okay, it has shifted to this one. Okay, next thing is I have to declare a component which is a full adder. So I'll copy the entity of full adder, say Control C, and go to my component and paste it just like we did for half adder. We are going to do it is for full adder like this, and to myself I'm going to put in a node. Okay, so first of all I'm going to make this a component. This is a component declaration. Is optional. Okay, and then I will say end component. Okay, once you're done with this, you add a reminder for yourself to that there is a definition of a full adder here. Okay, and just say save. Now in an n-bit adder, just open the file. I'm going to add a remark. This will be VHDL code for n-bit adder, right? And then I have to use the same library and stuff, so I can copy that from half adder from full adder. You have this library definition here, so I'm going to say Control C and Control V. Okay, after having done that, we are all set for writing this down. But okay, I'm going to add a variation to this. Okay, I'm going to introduce you to generic, and then bracket open, and I'm going to say n is a generic which is of type integer. So entity is also used to pass certain variables. So these variables either have to be integer or have to be a physical data type. So physical data type like time, integer data type like integer, right? So I'm going to pass that the width is 8. So default width is 8, and I'm going to put in a colon here. So this is how you pass on the width of the circuit, the width of the word. Okay, so now having done that, I can change this to n minus 1. So this will be 8 minus 1, 7 down to 0. This will be also n minus 1. Okay, so once I have done that, I need intermediate signals, okay, which will be carry outs or carry ins, right? So I'll put in carry in. Okay, so I will put in here signal. Okay, and I'll say C is assigned. Okay, std underscore logic. Okay, std underscore logic underscore vector, right? And then I'm going to say this is going to be n down to 0. Now notice C is going to be 9, because if you see, I am going to have a carry in, and then I'm going to have carry out. So besides 8 words, 8 bits, it's going to be one additional bit, right, of C in. So that's what is being done here. Now, having done that, what I'm going to write here? First of all, I'm going to say C0. Okay, so C0 is assigned cin, correct? And then I am going to instantiate 8 times or n times. So I want to keep it variable. For, I can say, so for so I have to put a label. Okay, so this label can be what label do I put here? F1. Okay, and that's the label. For I equal to 0 to 0 to, it has been long time I have written that. For I equal to 0 to, for, is this right? 0 to n minus 1, and then say generate. If there is a problem, I have a problem writing the for loop, and F1. So I have a, sorry, I haven't labeled it correctly. Syntax error. Okay. Okay, so I think it is this. Usually I get confused in programming languages. Okay, let me put it to pause. Sometimes I get confused. Let me make sure. It has been a long time. F4. Okay, I realized what I did. Okay, so we are back up again. Okay, so for I in 0 to n minus 1, so that's going to be the sequence. Generate and generate F1. So this is going to be a for loop which is going to be used for instantiating same component n times. So I'm going to say FA1 is a entity full adder. Okay, then I'm going to say port map, right? And then here I'm going to give here two inputs, which is going to be A0, or in this case AI, comma BI, comma sum, right? So the sum will go to sum 0, sum I, right? And then okay, so there is going to be again C in, right? C in going to be CI. Okay, sum I, and then there is going to be CI plus 1. Okay, and then port map ends here and this. So unless I have done a mistake, so I haven't. Okay, so this will go from 0 to n minus 1, and Cn would be generated out of it at the end. Okay, so this Cn is your C out, right? So this is a full adder which is instantiated 0 to n minus 1 times, right? So in this case 0 to 7, and the connections go from AI, which is A0 bit, to B0 bit and C0 as the input, sum 0 and C1 as the output. So this loop will keep on going till n minus 1, where it will be a n minus 1, b n minus 1, c n minus 1, and then sum n minus 1, and then c n, right? So that will be C out. So after you come out, you are going to assign. Okay, so the sum is assigned properly. Okay, all you have to do is assign carry, right? So you will say C out is assigned Cn, and that's it. So this completes writing. So what did we learn new here? We learned how to pass a generic to an entity, and that generic is now being used here, right, as in the vector lengths. So this is 7 down to 0, 7 down to 0. By default, this is going to be 8 down to 0 because you have to account for C out, which is Cn. So Cn is assigned to C out, and sum is assigned properly. Okay, so we are all set. I think that's done. So what we'll do is we are ready for simulation. So we are going to hit simulate. Run simulation. Okay, so first of all I'm going to reduce this, and then I don't want to look at this one, so I'm going to press delete, and I'm also don't want to look at this one, so I'll press delete. Okay, so what happened over here to sum? Okay, so that's the size. Okay, so let's look at one of these numbers. So we can try multiple numbers. So let's put here what numbers you want to try. I'm going to go to this one. Okay, so I'm going to write down what I'm going to try. I'm going to try 1, 4 added 2, 2, 5. So the result would be 5, 4, 9, and the result here would be 14, and the result here would be 2, 1, 3. So remember, this is a hex number. Okay, so I'm giving 14 as a hex input, 25 as a hex input, and the sum is going to be this. Then the next thing I want to do is A9, okay, D6, and the result is going to be 6 plus 9 is going to be 15. 15 is F, and then A plus D. Okay, A is 10, D is 14, E is 15, right? So D is 14. 14 plus 10 is going to be 24. 24 minus 16, that is going to be 8, right? So you will be left with 8, and the carry it will give us 1. So this would be carry. So I'm going to try these two numbers, one this way and one that way. Okay, so let's go here, 14 and 25. Okay, so I'm going to go here and say fixed constant, force a constant, 14. So that's a hex number 14. And then this would be a hex number, force a constant, this is a hex number 25. 25. So this is what I'm going to do here, 14 plus 25, and say okay. And then carry in I'm going to give as 0, force a constant, carry in is a 0. Later we'll check with the carry in also. Say okay. So what result do I expect? Okay, so let's see that. Oh, it did for 400, doesn't matter. Okay, so I say 14, 25, 39, C in is equal to 0, C out is equal to 0. So if I give one more, then it will become 3A, right? So if I give a C in here, force a constant, if I give this as 1 and say okay and run this again, and if I do here, okay, so this will be 14 plus 25 plus 1, which is going to be 3A. So that's correct. Now let's try another thing is, I want to try A9 and D6. A9 and D6. So I'm going to force this to A9. A9. And then I'm going to force this to D6. D6. Correct? And then I'm going to force this to 0. Because I know that this is working, right? So I need not worry about this one. So this is forced to 0. And then I'm going to hit again. And I'm going to say view all. So I'm going to get 7F. 7F. D6. A9, D6. Let's see if our addition is right. A9, D6. A9, D6 and 0. So this is correct. F carry is 1. no, carry is 0. Then you have got A as 10, B is 11, C is 12, D is 13, not 14. So 13. 13 plus 10 is 23. So here our mistake. So this is 23. 23 plus 16. 23 minus 16 is going to be 7. Right, and the carry is 1. So answer is going to be 7F with a carry of 1. Let's see that. So C out is going to be 1 and 7F is the output here. Okay, so this basically completes our testing of this. Now if you look at here, there are going to be instantiations. Okay, so let's go back. So let's close this simulation window. Say discard it. Okay, so there's going to be a little elaborate description here. Okay, let's go ahead and synthesize this. Okay, so you go here. Okay, meanwhile, if you want, you can also look at the schematic. Kind of slow. Okay, so you can always go down in hierarchy. For example, if I double click this, it would go down in hierarchy. So you see what I did? A B sum carry. You see here is the same as over here, right? This is the same stuff as this stuff, right? There's a R at the output. There's a sum carry coming out. So C0 and C1 go here. Sum 0 goes in here, right? C in goes in here. Sum and C out. So that looks okay, right? So how do I? So basically, that's all. What I wanted to show you is schematic. So I'm going to close that. Close elaborated design. Okay. So now. Okay. So I have closed the elaborated design. Now I'm going to run synthesis. Okay. Say okay. So over here at the top, when it's running the synthesis, it'll tell you. So it's running synthesis here. But meanwhile, it has opened something over here. Okay. What you should see is window and look at the I/O view. There has to be constraint definition here. Open an I/O here. Well, let's synthesis finish. I think you can open that window even before that. Tools, window, IP, properties, messages, log, reports, layout, view. Report. Maybe it is doing something, that's why it's not visible. Specify constraints. Where is constraints? It should be under tools. Reports. window. Okay, open synthesize design. Okay, this is what your FPGA is, and you can't see much here unless you implement it, right? This is just the device. Let's see, where is IO constraint, IO planning, right? Is it called IO planning now? It used to be called constraints. IO. Just one second. Let me put you to it because this is a new version. Okay, so this looks something new. So what I'm going to do is I'm just going to follow and see if something goes wrong. So it says autoplace IO ports. Let's see how it is. Say next. 26 ports will be automatically placed. 8 plus 8 is 16, plus 8 24, 24, and then 2 of them, one is input and other is output. Say finish. So let's see what it does. Okay, so where do I see those? Tools, port editor, property editor. Okay, messages. Okay, let me put to pause because this is something new which I'm seeing here. F4. Okay, so what has happened is it has tried to do its pin assignments, which I don't agree with. So if I go to Windows and go look at IO ports, I have to assign these ports properly. Okay, so this one is going to be V10, so I have to unassign all this. Okay, so basically this is going to be V10 U11, so that's how it'll go. So it should be V10, sorry, V10. Then so you look at the already, would you like to continue? No. So everything is messed up here, right? So this is all messed up. Okay, so what I'll do is let me just clean this up, okay, and then I'll come back and assign it. Okay, so what I'm going to do is I'm going to put you on the pause. Okay, I'll find out the right way of doing this, but okay, so what I had to do was I had to unplace all these ports which it automatically placed. So I have to place them on the board, right? So on the board you can see they are numbered from here. So I'll go with A7 to A0, B7 to B0, then I'm going from sum 7 to sum 0, and then carry over here, and then I'm going to use one of these pins as a carry pin, right? So that's what I'm going to do here. Okay, so that's also over here if you see in the data sheet. So in a data sheet, okay, so that's there. I should start from switches from V10. Yeah, I should start from V10, right? Okay, so I'll start from V10. So this is V10. Okay, so I'll put you on hold, and I have to just number these pins. So I don't want to take your time. So I'm going to put you on hold here and come back once I've done it. So I'm going to put F4. Okay, welcome back. What I have done is I have done the constraints. Okay, so these are called IO constraints. So I have put assign A7 to A0 from V10 to T8, and then B7 to B0 as R13 to R15. So this is as per this diagram over here. So these are the set of switches. These are 16 switches going from V10 to J15. So we are going from V10 to J15, and then there is going to be these LEDs which are going to go from U16, U17 up to H17. So they are going up to H17, and then there is a carry in which is used here as one of this pins as carry in, and then there is a carry out which is V11. Okay, so after having done that, what you do is you change the voltage level to 2.5 volts here. Okay, so not 2.5, LV-CMOS 33. So everything is changed to, why there is a sign here, let me see here, 25 is an error, 18 is okay here. Maybe on the board they have changed it. According to me, these were 3.3 volts. I think on this board they have changed it, so I'm still going to stick to 3.3 volts. Maybe in the new board they have changed it. In my old board it is 3.3. Okay, I don't want to burn my board, so what I'm going to do is I'm going to find my board exactly. So I'm going to go to NEXYS Nexus 4 DDR manual, because I don't want to blow up my board, right? Nexus 4 DDR reference manual. So that's one. Okay, so that opens that. That means I have to check what these are going to be. According to me, they are 3.3 volts. So these are IOs are 3.3 here, right? Let's check the new board. Let's check the new board here. New board. Let's see what did do to the IO. USB host here. It still says 3.3. See, all IOs are 3.3. Isn't it? Okay, it says Nexus A7 features overcurrent and over voltage. 5 volt Zener diode applying a power. Okay, so I'm going to just use LV-CMOS 33. Okay, and I'm going to save the constraint file, save constraints, save, and okay, and I'm going to give this a name. Okay, I will call this as text header. So okay, so that constraint file is saved, and still these are star. Star means what? Is there a warning? I'm not sure. I'm going to just try it. So after this, I'm going to run this synthesis again. Say okay. Okay, so it is running the synthesis again. So I'm sure that my pins are 3.3 volts, not 1.8 volts. Vivado is complaining for this particular device. Let's see what happens. Okay, so this is time consuming. Should I put you on pause? So I will put you on pause when it's done. Okay, so as soon as this comes up, you just say run implementation and say okay. So now it is going to implement this design. Okay, so I'm going to put you on pause again. Okay, so after this comes up, I can open the implemented design. So to look at how this is routed and these are placed. Okay, so is there a voltage violation? Where did I see the voltage violation? 5 warnings. Voltage violation. Not in timing mode. Timing, power, junction temperature, watts. Is there a voltage violation? Is exceeded. Maybe is the voltage violated? Okay, so we'll see this later on. Let's see what has happened. Okay, so here is our design. So if I zoom in, okay, so this is I have used this way. So I want to show you the connections. Okay, so this is our connections here. So I can zoom out. Okay, so these are our IO pins, and I'm utilizing something over here. So this is what I have utilized, right? So this is how it has placed. It is not optimized, but you see all these switching matrices and CLBs, right? So if you zoom into a particular CLB, okay, so you are going to look at lookup tables, marks, and everything what I was talking about, right? So this one is a lookup table, right? So this one is a lookup table. Okay, and here, oh, come on. So this is all our design. So you see it hasn't taken much space here. It's just that the IO are completely utilized. Okay, so now I'm going to say generate bit stream. Okay, generate bit stream and say okay. Okay, so I'm going to put you on the pause again. Okay, so we are back. It has done this, and what I will do is I will go to Open Hardware Manager and click OK. Okay, so now I would have to put in my device to the USB port. So I've done that, and I have to connect my device. Okay, so I have to connect my device. So let me just 1 second. Let me show you the device first. Okay, then I go to F2. Let's see if I'm looking at my device right now. Yeah, so I'm looking at my device right now, right? Okay, so let's focus on that. Okay, so now I have to connect my device, and that device is connected from here. It's connected to this port, and so it is going to go this way. So this is connected. Okay, by the way, it was on. Hang on. Okay, so this is built-in self-test, and these are the switches right now. They are configured this way that whichever you turn on, that LED will turn on, right? Now I'm going to program this. So to program this, I have to just go to open target to connect. Okay, it says found the device. Okay, and then you have to hit program device and say program. So once it's programmed, this LED comes up. So now this is programmed. Now what I'll do is I can give inputs, right? So this is my A input, so I will put here 1 4. So this is 1, and then this is going to be, so this is 4 bits, and then this is 4 bits, so this is 1 4, right? So 1 4 plus 0 is 1 4. Is that right? Yeah, 1 4 plus 0 is, so then I have to do 2 5, right? So this 4 bits, and then this is going to be 2, and then this is going to be 5. So the answer is going to be 2 9, isn't it? So let's see, what did you have here? 3 9, right? So yeah, so the answer is 3 9 here. So you read here, this first 4 bits is 9, and then this is 3. So if I press this one and 17, then the carry in would be 1, then it will be A, right? So this answer is, the answer is, say here A is 1 4, and then the B is 2 5, and the answer is 3 9. And if I give in here N17 as 1, then this becomes 3A, right? So this basically validates what we have been doing, right? Similarly, let's do other word. Okay, so the other one word was A9. Okay, so let's put there A9. Okay, so this is going to be A, and then after 4 bits I have to put here 9. So this is A9. Then I have to add here D6, right? So C is going to be 12, and D is going to be 13, D, and then I'm going to have 6, right? So this is going to be 6. So this answer will be F. So the lower 4 bits are F, and then there is this 7, and then there is a carry out. So 1 is the carry out, and 7F is the answer. Now if I give in here 1, then this will become F will become 0, and then this carry will come here, it will become 8, right? So this become 8 0. 7F will become 8 0 if I give in carry in, and then there will be carry out of 1. So basically this completes our exercise, and I'm going to stop here, right? So let's do this. So if you want to stop this, what you want to do is you want to first disconnect from the server. So I can see here, file, close hardware manager, okay, and then switch this off, and then let me get back my this. Okay, so now I have done that. Okay, so you have seen the results. So what I'm going to do now is I'm going to end this session over here. So I have shown you the complete flow of synthesis, right? So thanks a lot. Thank you very much.